also learned that it's also called a normal distribution. You'll kind of mean data piles up in the middle is approximately the same on either side. Okay. They have a mean of 100 and a standard deviation of 15. Okay, so let's do some writing. So our variable here, okay, our variable here is an IQ score. They have a bell-shaped distribution. Mean of 100, standard deviation of 15. Okay. What percentage of people have IQ scores between 70 and 130? What are we going to do? So we left off a week ago with this info. I'm going to maybe go back and review your notes just a little bit. And you know, if you're taking notes around the note sheet, what you might do is you know, do like numbers. Like if you're to correlate, you know, whatever notes are in your notebook to that in the packet, you know, do a 1. Maybe how far are these values, right? Smaller than the mean, bigger than the mean, agree? Yeah? So how about their distance from the mean? You with me? Yeah. Yeah, how many standard deviations? Okay, so take 100, subtract 15, are we there? We would be at 85, right? Subtract it again, we there? Yeah, so the 70, and this is number 29, the 70 is the mean minus 2 standard deviations, right? Or 100 minus 2 times 15. Do you agree? Does that make sense? Do you remember? Kind of, sort of? Throw me a bone here? Okay, cool. On the other end, 130. Take 100, add 15. We there yet? No? Add another 15. We'd be at 115, right? Add another 15. Are we there? Yeah, good. Okay. So the 130 is the mean plus 2 standard deviations, or 100 plus 2 times 15. Okay, so the magic number here that you want to pay attention to is how many times did you add and subtract the standard deviation, and then just apply the rule. So what is the, and here we're talking empirical rule, right? Because we have that bell-shaped distribution. Okay? You need that information in the problem. Bless you. You need that information in the problem to be able to use the empirical rule. If you don't, then just use Chebyshev. Okay? So what does the empirical rule say about 2 standard deviations? How much data? Look it up. 95%. Perfect. So then we can say that 95% of people have IQs between 70 and 130. Okay, you guys with me? So far so good? Okay, so now what percentage of people have IQs less than 170 or greater than 130? So 95% of people are between these two. How many are less than 70 or greater than 130? The other 5%. You with? Yeah? Okay, cool. So part B would be 5%. And part C, what percentage of people specifically have IQs greater than 130? What do you think? 5% less than 70 or greater than 130. So how many specifically greater than 130? 2.5%. Good. when you have that symmetry, you guys, or that bell shape, remember what that indicates, that the distribution is the same on either side of the mean. You could fold the distribution across the mean, and the halves would pretty much lie right over top of one another. Now, no, it doesn't have to be perfect. We're still good to go here. So we'll learn kind of more about how this thing ekes out along the way. Okay, so 2.5%, good. Cool. All right. Here we go. Same page. According to the U.S. Census, the mean time of the mean commute time to work for a resident of Boston, Massachusetts is 27.3 minutes. Assume that the standard deviation of the commute times is 8.1 minutes. Now note, does it say anything about the shape of the distribution? No. I'm not going to tell you use Chebyshev's or use the empirical rule. I want you guys to figure that out by the problem, okay? So now, we have that our variable is the commute time for a person living in Boston. Boston. Okay, mean is 27.3 minutes. Standard deviation is 8.1 minutes. Okay. What minimum percentage, and recall that Chebyshev's has stated that at least whatever percent is within k-standard deviations of the mean. At least. So that's why it says the minimum percentage. Yeah, Joanna?
What page is this on?
It is, I have 140. It's in 3.2. There's gonna come a time when our pages don't correlate.
It's 154.
It's 154? I guess that time has come. Thank you. 154, Joanna. 3.2 at any rate, that problem was in 3.2.
It is.
Because we have a custom book, because some sections we just left out, and we didn't want the students to have to pay to have those sections copied, because we have the paper bound, so that the pages of yours and mine got out of whack. Okay, so what the minimum percentage of commuters in Boston has a commute time within 2 standard deviations of the mean? Read your rule. What does it say about 2 standard deviations? How much? 75%? Cool. So 75, shall we say at least 75% of Boston commuters have commute times within 2 standard deviations of the mean. Okay, what minimum percentage of commuters in Boston has a commute time within 1.5 standard deviations of the mean? Oh, okay. So, I didn't calculate this on your handout. So, you may have to do this once or twice on your homework, but I wouldn't ask you this on a test. So recall that in Chebyshev's theorem, so the number of standard deviations away from the mean has to be at least 1. So it has to be, no, I take that back. Strictly more than 1, strictly greater than 1. Okay, so here the K, you're talking 1.5 standard deviations of the mean, and we want to know the percentage. So here you have to use that little formula. So it would be at least 1 minus 1 over k squared. So if the k is 1.5, it would be 1 minus 1 over 1.5 squared. What do we get there? You guys help me out? You guys have a good long weekend? Get a little more sleep? Make a little more money, work? Something? Looks like about 56%, 55.5%. Anybody else get that? You should be working along. About, so about 55% of Boston commuters have commute times within 1.5 standard deviations of the mean. Okay, so now what are those commute times? So now we want the interval from what amount of time to what amount of time are you going to find that 55% of commute times? What are the actual times? What are you going to do? What are we going to do? Somebody help me.
Repeat the question.
Say?
Could you repeat the question?
Sure. So we want the interval of numbers, okay? So we want 55% of Boston commuters have commute times between what numbers? That makes sense? So you have to actually find the interval of times, from what time to what time, what amount of time. Yeah?
Would you multiply 8.1 times 1.5 and then add it and subtract it to the 27?
Yes, perfect. Yep, you got it. Perfect, perfect. So our lower bound, we're gonna take the mean and subtract 1.5 standard deviations. And for the other bound, we're gonna take the mean and add 1.5 standard deviations. And by 1.5 standard deviations, I mean, as our friend here pointed out, 1.5 times the standard deviation. Yeah, good. So we've got 27.3 minus 1.5 times 8.1. And the upper end is 27.3 plus 1.5 times 8.1. Yeah, good. Yeah, Chris?
Is it multiplied by the 8.1?
Why is it?
Yeah.
Because it's, you're gonna go out one standard deviation and then another half of a standard deviation. So it's 1.5 standard deviations, or 1.5 times the standard deviation. Yeah. Would you put your drink? Thank you very much. Okay, what do we get? Anybody help me out? If you don't have a calculator on you too, you can find one in the accessories on the computer. Do you know where that is? I mean, you guys are experts at finding stuff when you want to, right? Go down to the little star thingy, the little Windows thingy, all programs, go to accessories, wherever it is. Wherever it is, wherever it is. I thought it was, but I didn't see it. I don't see, oh, there it is. And then calculator. And then if you want a scientific calculator, whoa, look at that puppy. So what do we get? What are our numbers here? Say again, Jen?
15.15,
15.15,
and then 39.45.
39.45, thank you, minutes. Does everyone agree? Does everyone agree? Does that look good? Okay, cool. Cool. All right, what's the minimum percentage of commuters who have commute times between 3 minutes and 51.6 minutes? Three and 51.6. So how are we gonna figure out the percentage between 3 and 51.6 minutes? Okay, how many standard deviations does it take to get to those? Yeah, actually, once you figure this out, it's probably right in your, it's probably one of the values I gave you in your notes. So you just have to figure out, take your mean of 27.3, how many standard deviations until you get to 3 minutes? 3 minutes? Man, I have a short commute time, I'm gonna have 3 minutes. I guess this maybe when your office is in your house, takes you 3 minutes to grab your coffee and walk over there. So what do we get? 3 standard deviations? Okay, thank you. So if you take the mean, the 27.3, and subtract 8.1 3 times, okay, we get to 3 minutes. Is that true? Okay, good. And then if we take 27.3 and add the standard deviation 3 times, we get to 51.6, is that right? Is that right? Okay, good. So the magic number here is, and what does your handout say about 3 standard deviations? 89%, isn't it? Yeah, good, 89%. So 89%, whoops, not 89. Boston commuters have commute times between 3 and 51.6 minutes. And you know, we can say a minimum of 89%. Yeah. The 3 standard deviations, if you take the 27.3, the mean, subtract 8.1 3 times, you're gonna get 3. Does that make sense? And then if you take the 27.3 and you add 8.1 3 times, and the 3, the number of standard deviations is what correlates to the rule. Okay? As we talked about last week, it's not the value of the standard deviation, it's how many of them that you have to add and subtract to get to those bounds. Okay? You guys cool? You good with that? Yeah? And when you're, you know, if you have issues when you're doing your homework, of course, just ask. Okay, so, 3.4. Our first exam is scheduled for next Wednesday. I think we'll be ready to do that. I think we're gonna finish up this chapter today. So, yeah, exam 1 next Wednesday. Maybe I should write that, right? You might start writing out your cheat sheet. You know, just as you go over stuff and, you know, pertinent formulas that we've used, the empirical rule and such, you'll wanna write down.
Cheat sheet, just a 3x5?
No, you can have a whole sheet of notes
Okay, front and back, awesome.
on the edge if you can fit stuff. My advice is don't put too much on your cheat sheet, because then you won't be able to find anything. It gets so cluttered, you're like, oh, I knew I had it here somewhere. Okay, roll sheet coming around, and again, today's transfer day, there's tons of universities and colleges out there to give you info. Thank you, Jen. Okay, so let's say that you got a B on your statistics test and you got a C on your bio test. But let's say to get that C in your bio test, let's say you scored a 72%. But let's say to get that B on your stats test, you actually scored a 64%. But your teacher curved the test, which brought you up to a B. So how would you compare these? You scored less, but you earned a higher grade. So how you would compare two values within their specific distributions, we would use something called z-scores, and this is 3.4. So it's called a standard score. You've heard of standardized testing? This is how they standardize. Okay? So, it's really important. We use z-scores heavily through the entire course. So it's really important to understand what a z-score tells you. And what it tells you is, and we were talking about variables and statistics, you got x's and y's and b's and stuff like that. But anytime you see a z, you know it's a z-score, specifically reserved for z-scores, okay? And what you do is you take the data value, you subtract the mean, and you divide the whole thing by the standard deviation. And what that gives you is the exact placement of that data value within the distribution in terms of standard deviations, specifically in terms of standard deviations, okay? So it gives you the exact placement of that score within the distribution in terms of standard deviations. And it's how far above or below the mean. If the z-score is positive, then that score is greater than the mean. If it's negative, it just means that that score is below the mean. Okay? Really important though, really important to understand z-scores and the fact that they measure in terms of standard deviations. Okay? Because we've been talking about in this chapter how data is spread out is really important. It's really important. Not all data is created equal. Let me give you an example here. Okay. Let's see. This is in 3.4. I'm not sure what page that is, but it's in 3.4, number 7. So how would you compare the height of a woman with respect to the height of all women, and that of a man with respect to all other men? So the average between 20 and 29-year-old man is 69.6 inches tall. And men's heights have a standard deviation of 3 inches, while the average 20 to 29-year-old woman is 64.1 inches tall, with a standard deviation of 3.8 inches. So who's relatively taller, 75-inch man or a 70-inch woman? So when they say who's relatively taller, it means with respect to their peers, within their each individual distribution. Does that make sense? You guys with me? Okay. So which men's heights or women's heights, which of those distributions is more spread out? Say? Men or women? Men? Women? I do one singular and one plural, that's not good. Okay, guys, 69.6 inches tall on average. Standard deviation of 3 inches. Women, what do we have? 64.1. Standard deviation of 3.8. Which distribution is more spread out? Women. Why? Bigger standard deviation. Okay, so he's 75 inches tall. So, meaning that one individual male, yeah? And she is 70 inches tall. Now, to compare them relative to one another, well, he's taller, but of course, on average, men are taller. You with me? So it's who's taller according to their peers, as it were. So when you Z a data value, you're you're stripping off the units. You're taking values from different distributions and making them comparable in a like or same distribution. And that is how many standard deviations that value is above or below the mean. So 75, now note, he's taller than average, right? So his z-score is going to be positive. And that should make sense because in the numerator, right, if you take his value, his height, minus the mean, you're going to get a positive number because he's taller. And then standard deviation is always positive. Okay, what do we get there? Somebody, 1.8? Okay. So his height is 1.8 standard deviations above, because it's positive, the average men's height. So it's the number of standard deviations, and you have to specifically address above or below, okay? Let's talk hers. So her height minus the mean, she's also taller than average, divided by the standard deviation. And what do we get there? Sorry? 1.5? 1.55? Okay, so her height is 1.55 standard deviations above, again, because it's positive, the average woman's height. So who's relatively taller, him or her? He is, because his standard deviation is further above the mean of his distribution. That make sense? Okay? So you've made them comparable across the same, rather than apples and oranges. Oh, how about this? Rather than plums and apricots, now you have a pluot. Okay, let's try another one. In 2010, Josh Johnson of the Florida Marlins had the lowest earned run average. Mean number of runs yielded per 9 innings pitched. So, smaller is better, right, in an ERA? Smaller is better?
Yeah.
Yeah, okay. Of any starting pitcher in the National League with 2.3, also 2010, Felix Hernandez of the Seattle Mariners had the lowest ERA of any starting pitcher in the American League. His was 2.27. So what we're comparing is the lowest in the National League and the lowest in the American League. So which player had the better year relative to his peers? Can you guys handle that one? Take each distribution, the National and the American League. You want the mean and standard deviation, and you want each Josh and Felix's individual ERAs, and then find their z-scores. case, lower is better. It's how many, runs you allow, right? You allow the other team, is that correct way of thinking about it? You guys already know where you're transferring to? At this point in time, most of you do. You have a plan? Still thinking about it? Probably have till next fall, right? Is anybody transferring in January? Transferring? Are you transferring in January? Well, where are you going? Humboldt? Beautiful. Humboldt, Chico, Sonoma State. You all have the distinction of being like the hippie colleges. Okay, in the national, okay, that's fine, I'm in hippie college, liked it. In the national, what was the mean? What do we have?
3.622.
3.622, cool, what was standard deviation? 743, everyone agree? Everyone agree? And what was Josh's ERA? 2.30? Okay, so we take his score, subtract the mean, divide by standard deviation, and what do we get?
Negative 1.77.
-1.77? Cool, thank you. Now note, negative because his ERA is below the mean. Right? Right? Everybody good? Okay, cool. Okay, how about Felix? What's the mean of the American League?
3.929.
3.929? Is that right?
Yeah.
Cool, thank you. And standard deviation?
775.
0.775? Great, and what was his ERA? 2.37?
2.27.
27? Okay. So to find his Z-score, take his ERA, subtract the mean, divide by standard deviation. And what did we get?
Negative 2.14.
Negative 2.14? Okay, so who did better ERA-wise?
Felix.
Remember, lower, smaller is
Josh.
better.
Josh did better.
Smaller is better. Because it's farther below the mean in this case. Does that make sense? Yeah. Did better. His Z-score is Cool. Okay, so that is Z-scores. And again, those are gonna be really important to us. Okay, so another way we can look at, oh, I was gonna say, like, if you look at standardized, like standardized test scores, like, a lot of, like kids in grade school and stuff, and I guess, you know, 8th grade and stuff, they do a lot of testing, they compare the scores of different schools. They're all standardized, meaning they're all put on the same playing field by standardizing the scores. So they're comparable with other schools, with other districts, etc. And that's a pretty common thing to do. Okay, so another way to look at position is with percentiles. Okay, so percentiles, percentiles are, if you could ideally divide the data up into 100 little compartments, smallest to biggest, where like 1% is in each compartment. And you would have 100 of these. Okay? You would have your smallest or your minimum score at the very lowest end. And then P1, the first percentile, would be such that 1% is at or below, 99% is at or above. Meaning 1% is smaller, at or smaller than that number, and 99% is larger, of the data is larger or greater than that number, okay? Like P2 would be such that 2% of the data is at or smaller than that number, 98% is at or larger, and so on and so forth. So like P60, 60% of the data is going to be at or smaller than that number, 40% at or larger. Does that make sense? Okay, so those are percentiles. So like if you took a test and you scored in the 88th percentile, you know you scored at or better than 88% of the other people who took the test. 12% scored at or better than your score. That make sense? You guys with me? Okay. We can also look at data in deciles like decade, where instead of 1% in each little compartment, you have 10%. Whoops, that's a 1. And so here would be your smallest value, or the minimum. Here would be D1. Here would be D2. And you've got 10 deciles. So if you're at D1, 10% at or below, 90% at or above. D2, 20% at or below, 80% at or above, and so on and so forth. But the type of percentiles that are going to mean the most to us are called quartiles. So quartiles divide the data into fourths. And let's be more specific, they divide the ordered data into fourths. So you've got 4 little compartments. The smallest 25% goes in the first compartment. The next largest 25%, and so on and so forth. And the largest 25% of the data goes in that last compartment. So here's your smallest, we call it the minimum or the min, generally, is the lingo. And that's